scheduled fire alarm this evening. Colin, I was going to sit there. Could I sit there? Could I sit there? Could I sit there, Colin? Is that okay? Okay, thank you very much. You can sit there. You can sit there. There's no scheduled fire alarm this evening, so if the fire alarm goes off, it's not a test. If we could all leave by the main entrance, which is out of this door, then turn right straight out onto the pavement, and then turn right down onto the corner by one of the buildings of the German embassy, I noticed this evening. I've had no update from Rugby, and I just checked with Gareth earlier this evening. So apparently we're very close to signing the lease on the rooms upstairs, and when we do, it'll be fantastic. But we haven't moved along. We've moved along a bit since last month. If I click on, I can tell you about our events for this year. If that works, is that going to work? Is any of this going to work? I've broken it, Gareth. Oh, oh no! Oh, lordy, we don't want that at all, do we? Stop that. No. Let's try again. No. Yeah, there we go. Fantastic. So last month's presentation, case study in separation problems and solutions from Tom Ralston of MICEP. Last week we had our one-day seminar, which was revenue generating for Song. That was LNG and alternative fuels for shipping. That was very successful. That was at the IMechE. And I think everybody who attended enjoyed it very much. So this evening we've got use of compact heat exchangers by Phil from Alfa Laval, and I'll introduce him in a bit. Next month, March the 10th, we've got a presentation from Arca Solutions on asset digitalization. April, we've got a presentation from Tullow Oil on inclusiveness and diversity. 12th of May, presentation on Platform of the Future by Jonathan Montgomery of BP. June's presentation is open. That'll be our AGM, so we'll fill that with something shortly. And then October, we've got a presentation from Johnny Keane of Arca on decarbonisation of LNG. As you can see, we've still got some slots to fill in, so we'll do that shortly. If I go back up. Okay, so that's programme of events. We've got a short presentation to start with from John Mosley on super compact separation, and then I'll introduce Phil, as I said, from Alfa Laval. So if I escape from this, and then I can probably put up your presentation, John. So this is... Okay. Yeah, John, there you go.
Thank you very much. How do I click on?
It should just be up and down.
Up and down. Yeah, good evening, everybody, and thanks very much for the opportunity of this slot. I'm John Mosley. I'm a chemical engineer. I started my career about 100 years ago at MW Kellogg that Richard out there somewhere reminded me of. And most of my career I've been working for process technology companies, most notably a company called Natco. I was sales director for Natco for about, well, several years, and that's all part of the Schlumberger Group. Around about 5 years ago, I had a bit of time on my hands when the last downturn, and I've had this idea for some time, and I thought if I don't try it now, I'll never know. So I've conceived and developed a super compact separator. Last year, we got on this OGT, the Oil and Gas Technology Centre in Aberdeen. We got on their business accelerator program for potentially companies with game-changing technology. So I spent a lot of time in Aberdeen last year, meeting operators and so on to present this technology. And we've just been told we're on the shortlist of the SBE Offshore Achievements Award for the emerging technology category, which is a big award ceremony in Aberdeen next month. The principle I've got is, what is it? It's turbo powered, and it's revolutionary because it actually revolves. So it is revolving technology where we're using the pressure of the well fluids to power a centrifuge, essentially, to give you high separation efficiency in a residence time of about 1 second. This, am I going to run the video? There's a video in there somewhere. Oh, it is running. What this jumping video is actually showing is this is a full-size proof of concept unit on simulated produced water. So this is 2,000 ppm of oil. What you can more or less see in the jumping slide is the oil spinning to the middle, and we're taking it off this line here, very similar to the principle of hydrocyclone. So the full-scale proof of concept unit, this was tested at a commercial test facility in Europe. It proved the principle. This animation shows how you could incorporate the technology into the oil and gas sector. So it started and it's jumping a bit. So application one is to de-bottleneck your oil field. So most oil fields are now producing 4 times as much water as oil. One of the bottlenecks is existing hydrocyclones. Quick retrofit of that existing vessel, put our magic tubes in, bolt it back up again, fire it up, and we can now process up to 4 times as much water as that existing hydrocyclone. How this might work is a well where the well pressure is going down, water cuts going up, revenue's going down because you can't produce the crude. Take out the cyclones, put our tubes in, relieve the water, get your revenue up. This could actually extend the life of your field by 5 to 10 years. Application 2 has a super compact production separator where for what in the OGTC is called the facility of the future. Conventional separator for 50,000 barrels a day, that is what ours would look like. So on most production trains, you've got an HP, MP, LP separator, big vessels, big deck space, big weight. We believe we can magic away at least 2 of those, put our super compact separators in their place. So that could be game changing for new field developments where we can bring down the size and weight of your new facility. So instead of that, you've got that. I'm leaving the HP separator in now because I'm not, I'm not going to guarantee everything, but that in itself, if we did that, you're going to save 50% of your weight of your top size modules and 50% of your deck space. The technology also you could consider using as a tieback. The subsea community's got very excited in Aberdeen, and on an FPSO, its performance isn't affected by pitch and roll. And also looking to the future, could even be considered as a downhole separator, get the water out downhole and dispose of it there. So oil and gas is our stepping stone, but the application is also many markets: pharmaceutical, petrochem, nuclear. We're on a schedule now. Our full proof of concept units built. We're now in a 12-month program to design and build a pre-production unit and a field test unit for field testing early next year. So we're now in the Aberdeen fraternity. We're putting together the support of the OGTC and other operators, service companies, And support is welcome for peer review, benefit and kind support, JIP, or a bit of money may even help. But that's rolling ahead right now. And I think that's it. Thank you very much. Join us. It's revolutionary. There are some of these on the side there.
Okay, and John, you'll be around at the end if anybody's got any questions or wants to chat with you. That's fantastic. Thank you very much. That's great. So if I just swap over again, I've got the sign-in sheet, so I'm going to come around and pass them all to you at the end of the row, if that's okay. If you could, I know you probably signed it on the door, but if you could sign in on the sign-in sheets, that'd be fantastic. And then we've got a record of that one. You're doing something clever, Phil. Okay. Is that what you wanted? No. No, it's okay. No, I'll step on. Let me hand out the sign-in sheets while we're going. Okay. Colin. Yeah. No,
I might need to change this, maybe.
Do we need to all this stuff?
Do you have an HDMI cable?
Sorry about this. I think we're going to have to set it up. Go old school. Do you know where you We're going to give a quick share one more go.
You'll need a mic.
So that's the one we use.
I'll hand you this one. Right, we're all ready now. Phil's got 2 laptops, so he'll be clicking twice. Thank you very much for being so patient. It's just having a final polish tweak. Do you get paid enough for this job, Gareth? Fantastic. So Phil Sigari is here from Alfa Laval tonight. He's going to talk about compact heat exchangers. Phil's been with Alfa Laval for 12 years as a technical sales engineer. He initially worked with HVAC and light industry applications. And for the last 7 years, he's been involved in various refinery, oil and gas and other process industry projects using compact heat exchangers. So perhaps you could put your hands together, please, for Phil.
Good evening. Right, keep mine working. Just a little bit of a history lesson for those who don't know Alfa Laval. We were formed in 1883 by a Swede called Gustaf de Laval. The headquarters are in Lund in southern Sweden. It's also our main production facility for gasketed plate heat exchangers. We are a worldwide company. We've got 39 production facilities dotted around the world and more than 100 service centres and dedicated sales companies in 55 countries. Alfa Laval are split into 3 industries: heat transfer, separation and fluid handling. I'm in the heat exchanger, heat transfer section, in the energy division. Compact heat exchangers. We've got probably one of the widest ranges in the industry. When people say what the limits of the limitations, usually it's to do with pressure and temperature. So this is an overview of our units. See, we've now got a PCHE heat exchanger range, and then all the way down to the more standard gasketed and various welded units in between. So what makes a compact heat exchanger compact? We often get questioned why our units are so small compared to shell and tube heat exchangers, and often a notion of disbelief that they will perform. Higher K values can generally be achieved, thus the area is smaller than an equivalent shell and tube. As shown here, a typical water-water duty for a plate heat exchanger, the K value is 7,000 watts per meter squared K. Let's say we double that for a shell and tube. So if we use the formula U equals K times A times LMTD, the same duty requirement, a higher K value equates to a smaller required area. And to make this happen, our plate heat exchangers have very thin plates. Some of our units now go down to 0.3 millimeters thick. The mechanical strength is actually provided by the chevron pattern and many contact points, making quite a rigid block. With the channel plates, you imagine these one put on top of the other and up the other way. The flow path is like a corkscrew effect, which creates a high turbulence, a small laminar wall film, and minimizes fouling. Because we use counter-current flows in our exchangers, we can get very close temperature approaches. It says here down to 3 degrees. You can go closer, but the size of the heat exchanger will exponentially get bigger. So gasketed heat exchangers are used in many industries. The main ones I deal with, I won't go through them all, but it's oil and gas, power, HVAC, pulp and paper, and metalworking, just as a few. So gasketed heat exchangers are made. They've got a frame plate and a pressure plate which sandwich the channel plates together to form the plate pack. This is supported by a carry bar at the top and another bar at the bottom, and then clamped with tightening bolts, as the picture says. To give you a little idea on how they're put together. Yeah, so if you can do a plate back up that quick, you're doing well. And the flow paths in them is shown as thus. So this shows a counter-current flow, but you can have a co-current flow with both fluids going in the same direction. Often that's preferred in some oil duties, crude oil, and also in some fine chemicals where the plate wall temperature is important to avoid any waxing or product degradation. Okay. Our gasketed plate heat exchangers, we have fixed plate sizes. So in the instance of very high theatre duties, it's possible to make multi-pass designs, as there's no plate that fits every single duty. So having a multi-pass, you can increase the surface area and save space, in effect, by making the plate taller than what it actually is. So limitations, pressure and temperature limits due to gasket materials are probably, compared to shell and tubes, one of the two biggest. We are limited to 180 degrees with Viton gaskets. We are developing something a little bit higher, but that's only 200. And the standard gasket range, the big units go to 30 bar. If you go to semi-welded, you can go up to 55, 60. And then being a unit with gaskets, they can wear through time and they need replacing. But then the exchangers are easy to open. The flexibility and benefits, you can have many different plate materials, 304 and 316 for HVAC duties, all the way up to titanium and D205 for process duties. Okay. The other heat exchangers in our range can be considered as welded. Now, which one you choose depends on your duty and whether you're liquid or condensing, and also whether the unit needs opening for mechanical cleaning. Many of our units are sealed and can only be cleaned by chemical methods. The smallest one of our ranges are copper brazed unit. These are mainly used in heating and ventilation units. They're made by sandwiching copper sheets between the stainless steel channel plates. They're clamped together and they're put in an oven, and it brazes the plates together. This method eliminates the need for seals and thick flame plates, so they're quite compact units. So the benefits of these are low capital investment, a small footprint, and low investment costs, installation costs. Unfortunately, copper is not really great with a lot of fluids, so often makes these non-suitable. And as I mentioned, residential heating, heat pumps and engine cooling are their main areas of use. Moving on from the copper braze, we've got our Alpha Nova unit. This is similar, but it's 100% stainless steel unit with a wet diffusion method used instead of brazing. It can be considered 100% stainless steel, means it's got a high chemical resistance. Again, that's just a list of some of the commonly used application areas. It's just a graphic there showing that when we go through the fusion process, there is a high degree of homogenization in the plate. And the reason this was developed was, see, copper can't be used with lots of some fluids, so nickel brazed units were weaker. With the Alpha Nova, gives you a comparison to the fatigue cycling, both pressure and temperature. And generally the Alpha Nova comes out quite positive. So moving on to the next unit, the Compo Block. It's probably the stalwart of our welded range. It's a fully openable, welded, compact heat exchanger. The two media in the Compo Block exchanger flow alternatively in welded channels. They consist of a square plate pack, well, small square plates welded one on top of the other, and they're sandwiched with top and bottom heads and panels. The plates are corrugated, but they're at 45 degrees, and then putting one on top of the other gives you a cross pattern, and it gives you the same corkscrew effect as a standard gasketed unit. The standard plate materials on these are stainless, SMO, titanium, and various Hastelloys. As mentioned, it's fully cleanable and is a proven challenger for shell and tube heat exchangers. Can be used across a wide range of duty types, and we've got an installed base of over 35,000 units. And another little video on how it works. As you can see, there's quite short plates on this unit, so to get the thermal length, we use multi-pass. And again, on the cold side. And the baffles shown here, we can move them to give different pass arrangements on each side of the exchanger. And this allows us to optimize the unit for different flow rates on each side. And the same units can be used as a condenser, but turned on their side. So this is a single pass condenser. And if you've got inerts in your system, we can deal with those with a 2-pass condenser. It works in a similar way to the first condenser, but then we've got a second pass where the inerts can go up through the channel. There are many more variants, but I won't bore you with all the videos there. And most of them are available on YouTube if you really want to go and have a look. So we can do a multi-pass vertical condenser. This unit here allows for subcooling of the condensate. We have the main condensing in the first pass, and as we get down to the lower sections, we subcool the condensate, and we can have a liquid level control on the bottom. Our CompoBlox has 7 models. The number, the designation is CP, and then the number is the width of the plate. So everything from 15 centimeters up to 120. The large CP 120s, we can have up to 500 plates. So they do get quite large. Again, the advantage is they've got a high thermal performance. So you can have a reduction in size and the number of heat exchangers. We can have a close temperature approach and crossing temperatures. They are a compact design, they're gasket free. And because of the high wall shear stresses, it's a reduced fouling tendency. And because the wetted area is small, when we can use non-corrosive materials. And the beauty of the CompoBlock is when you do want to clean it, you can take it apart, take the panels off the side, and it's 100% cleanable. If you throw a pressure washer through it along the edge, you've got channels where all the fouling will be flushed out, so all of the plate will be clean. Again, it's just a little picture showing someone who's taken one offline and given it a good clean. In the event of any failures, every single weld on the CompoBlock is accessible, so it is possible to repair the welds on them. Although we do recommend you use our welders. As this is a fully welded block, it's quite rigid. So we recommend the duties are stable. Cyclic duties will generally make the plate back act like an accordion. So you will fatigue the welds and they will break. And also to help avoid this phenomenon, a 2 to 3 bar pressure differential between the circuits is also recommended. This is just an example of a refinery we supplied to. They've got 14 CompoBlocks on site. 13 are installed, sorry, 3 are installed on the atmospheric distillation lining for cooling kerosene and gas oil. 2 are condensing overhead vapor on the pre-flash columns, and 3 are in the vacuum distillation column. All the CompoBlocks have been replacing shell and tubes since 1995. Previously, the shell and tubes had to be opened every year for inspection and cleaning, and they cost almost 10,000 euros per unit. with the exception of one of the copper blocks. Our units don't need to be open for cleaning. It's all done by cleaning in place with a 3% caustic fluid every 3rd year. This operation takes less than a day, and that would cost less than €1,000 per unit. Only the bitumen heat exchanger has to be opened up every year for manual cleaning by water jet. This takes 2 days, and because it's a corrosion resistant material, the local authorities don't require an inspection. Again, this is a copper block installed in Australia at an aluminium plant. The copper block is smaller. It does the same duty as the shell and tube behind it. It uses less materials. And again, another comparison. With this one, you've got the 3 copper blocks on the back do the same performance as the three shell and tubes at the front. The customer was a little bit apprehensive, hence he's got the 4th copper block there as a standby. And again, we've got you probably won't be able to see it on this slide, but at the top of that column, there's a small reflux condenser. Okay, the next unit is, we call it a DuraShell, but it's commonly known as a plate and shell exchanger. It's used generally in higher temperature and pressure applications. Again, it can be used in various operating modes: condenser, liquid, reboiler. We've got a relatively small range of 3 units. They can go up to 100 bar and a 450 degrees C with a carbon steel shell. If we switch to a 316 shell, we're limited to 350 degrees, but we can go down to -160. And going into the details, it's made up of welded plates put into basically a welded shell. And this is how it works. We like to do things slightly different with our unit. So this is actually a cross-flow exchanger. The majority of plate and shell units are counter current, but we can get an overall counter current flow by using multiple passes. Generally, with the DuraShell, we target these specific industries. In petrochemicals is batch reactor coolers and heaters, overhead condensers, interchangers, preheaters and reboilers. In the power industry, district heating, condensers, boiler feed water heating, air heating for gas turbines, gland steam condensers and performance heaters. And then in the oil and gas industry, TEG interchangers, gas compression, gas pressure reduction and LPG heating. This is just a where one of our units has been used in a new power plant in China. Its compact size and high thermal efficiency were the main reasons the company chose to go with the DuraShell. Unfortunately, with everything, there are limitations. Our units are limited to 316 stainless steel. There are titanium units available, and also our unit is fully closed. You can only clean it by CIP. So, moving on to the next one, our spiral heat exchanger. It's split into two ranges, the Spiral Pro and the Spiral Con. The Spiral Pro contains our liquid unit and our steam heater spiral. The Spiral Con is basically various different condensers. The stack condenser can contain several spirals in one assembly, so you can have multiple passes. And another little video. The main area of use of the spiral is where fluids are fouling. This will show you why. The fluids are in a single channel, so when any particles gather at the bottom of the channel, the velocity of the fluid will increase, and as it increases, it acts as a self-scrubbing effect and will eventually remove the fouling. It's typically used in pulp and paper and MEG applications. And if you do need to clean it, you can open it up and pressure wash it. Although we do have a range of standard off-the-shelf spiral heat exchangers based on heat exchanger area, most units are designed specifically to form a specific duty. The picture there shows where we've cut away the spiral to repair a hole in the plate. So it doesn't matter where the damage is, we can repair all these units. And again, a comparison of where spirals have replaced shell and tubes. The last unit in our range is the printed circuit heat exchanger. It's used to provide this. It's the smallest heat exchanger with a high thermal efficiency in clean high pressure duties. Typically, the targeted applications are pressure vaporizers in marine applications and pressure gas coolers in offshore gas compression. They're very small units, so as such, the structural and support for them is very lightweight. When you install them, they can be lifted by a single lift. Their compact size makes them easy to transport. and they've got a very high efficiency. They're also got a very small volume. But on the flip side, they're only suitable for clean fluids. You need to have a strainer fitted to protect them. Because they're fully welded, you can only use clean in place. And like the combo block, you need to have a stable operation. That's a brief overview. Any questions?
I think is that working now? Yeah, it's working now. Yeah. Any question? Yeah.
A very interesting and wide range of exchanges there. On the ones that you can't take apart and inject clean, what sort of fluids do you use other than cost? Do you use citric acid or anything else that's compatible?
Yeah, I mean, it's their stainless steel on the Durashells, so anything that's compatible with that. Yeah, of course.
Mainly if you have them on gas filled or oil filled duty, the scale, citric acid, very good. Would that be okay,
Yeah,
do you
that
think?
should be right, yeah, in low doses.
Anyone else?
I'm interested in the compo block and how the cost difference between a shell and tube and a compo block. I'm sure the shell and tube is probably cheaper. Am I right in saying that? Or
It depends how you apply it. If you change a compo block like for like, then yeah, possibly the shell and tube with a lower grade material is cheaper. But what you've got to realise is that you can use the higher grade alloys in a combo block in a smaller space, so it's not going to corrode. And with the pass arrangements, what we find in a lot of retrofit applications is that we can go down the whole. Take a refinery, for example, where you can go down the whole crude line and modify the temperatures, so you can get the crude that's actually going back into the furnace is actually hotter.
so it's more of a specialized circumstance type exchanger rather than necessarily applicable to, if you've got plenty of space.
Yeah, if you've got plenty of space,
it's difficult to justify.
Yeah, and you're not worried about it.
Yeah. Okay, thanks.
Any more questions?
Sorry. I think if you're looking for alternates and you're trying to decide as a process engineer whether to specify a shell and tube or something a little bit more, I shall use the frame exotic, but they're not really exotic. Should we say specialised? You've got to take through life cost into account. If it's offshore, the weight difference can be very, very significant. So the cost of your exchanger is only an integral part. But if you're replacing something that's, what was the percentage? 4, 5, 6 times bigger, together with the fact that you've got a hold up of the inside it, which is also 4, 5, 6 times bigger, the amount of steel you need to pick that up and hold it, as in an offshore structure, is significant. So you're not talking about the cost of a piece of equipment, you're talking about a total cost. So it may cost 50% more, it may even cost 100% more, but it's much smaller, and as long as it's fit for purpose, very important, if it's fit for purpose, you might find its total life cost, including the maintenance costs, are lower. So you have to do a complete, I mean, like, as you would in plant design, you have to do a complete analysis of what is best in this particular case.
I will answer that though, with gasketed heat with gasketed heat exchangers, when we use them offshore in the crude oil processing, what you tend to find is later on in life, the water cut and the oil changes. So you can then redesign the plate pad, take out plates to keep the heat exchanger optimal rather than having something that's really oversized and fouling.
Rob, did you have a question? You looked as though you had a question. No, okay.
With shell and tube heat exchangers, they're obviously covered by the recognised codes, and the relief requirements and safety requirements and failure cases are pretty well established. Are they all pretty well established with those types of heat exchangers as well, especially the all-well?
Yeah, they're all built to, we build them to the ASME code. Most of the welded ones are to the ASME code and have then the CE marked to PED. Whereas the gasketed ones we do ASME or EN 13445.
Dare I say, there are a suite of API standards for different types of heat transfer equipment. They cover plate and frame, compact, welded, PCHE, double pipes, obviously shell and tubes, air coolers. And I can't think of the other one, but there are, and those are published standards. They were mainly also co-branded as international standards, which meant they were also co-branded as Euro norms, which is significant if you're building something in Europe, because you've got a standard to actually conform to.
Our spirals conform to API 66468. And our it wasn't working a minute ago. Yeah, and our gasketed ones we can comply to API 662, but I believe that's changing. You'll correct me if I'm wrong.
Any more questions?
I've heard this before, but I just want to check. Also, I've got you a duplex outlines. Duplex stainless steel is not suitable for plate exchange.
You can't press it into that because it will crack. Well, it doesn't crack. The surface ends up like a skin of an orange.
Philip, good presentation and well done with the technology there, a bit challenging. Sounds like the death knell for shell and tube exchanges, but surely exchanges are generally specified by the clients. You're seeing specific applications. How do you go on getting specified by your clients if you're effectively giving them a unique solution?
Very difficult. You have to speak to the end users. Yeah.
But that is a real day challenge.
It is, yeah.
People are looking at your solutions and say, unless they've got a problem like the bitumen plant and they've got all these challenges with the shell and tube exchanges, they decide then that they need an alternative solution and they come in for a retrofit where you sit very nicely. But in terms of maybe newly specified equipment, that's a bit more of a challenge.
Yeah, you have.
Adnan has asked, are the PCHEs 3D printed?
No.
Another one about the PCHEs. Information localized boiler PCHEs, and that's in relation to gas compression.
I don't have that with me, but if you get his details, I can get an answer.
Thanks for the presentation. What's a typical lead time for a compact block exchanger?
It depends on how big it is and what the extras you require. A standard mid-range one you can probably get in 20 weeks, maybe less. But we've had units go with really big offshore or process requirements. They go to a year.
Yeah. Thank you.
Thank you very much. Any more? Any more questions? Okay.
Yeah, the example you gave of the comfort blocks replacing exactly the same duty on a shell and tube. Is there a difference in the pressure drop between the two cases?
I don't know the ins and outs of that one, but this does come up a lot because people think we have a high pressure drop. We sort of.
I think it's an intense pressure drop, but obviously if the area has been reduced, so you've probably got more pressure drop per unit area, but you've got less area. So
yeah.
Maybe overall you've got less, or maybe overall you've got slightly more. I don't think that's the question.
I'll come back to you on that one.
Thanks.
What about, say, the 60-ton exchanger, which I was really interested in, CB120?
Yeah.
How much will that cost, roughly? Just a ballpark. Yeah, it's yeah, make it out. Yeah. Give me a ballpark.
I'll give you a ballpark. I'll check something before because
yeah. I'm just interested, you know. And how does that compare to shell and tube? You're obviously reducing the size and everything, right? Is there a big cost saving using your units, or is it comparable?
It's not exactly comparable because we're usually improving the process as well. So there's process changes when you're doing like for like.
Okay.
I think, as Colin said, if your exchanger might be more expensive, but if your structural steel and all your support work is less, then your total installed cost per that unit should be lower, shouldn't it? I think that's the point you're making, Colin. Yeah. Okay. Any more questions? Just one more online.
Apologies if I phrase this all wrong. How does a contractor rate a compact exchanger for feed design?
It's not hand, is it? If you come to us, we will size it for you.
I think I'm right in saying that HTRI have got a program that you could use for a generic sizing. It won't give you an accurate one because obviously all the vendors are form specific. In other words, it depends on their individual presses, but it will give you an idea of the sort of size you're looking at. Are you telling me HTRI's program isn't user friendly? No. There are lots of variables, and that's why you have to employ a heat transfer engineer. The other thing that I didn't say before is safety. On some plants, depending on the fluids and the pressures and all that sort of thing, you might be looking at the relative safety of different types of heat exchanger. It's another part of that equation of a variable that you've got to look at when you're making that analysis of the type of unit you're going to use.
One very quick one. I just noticed Packinox was missing. Is there a reason for that, or?
I was going down the line of compact. They're not generally. It's a bit too specialised, I thought. They're used in very specific applications. But if you've got one, let me know, because I want to visit the factory.
Is that it? Yeah, sure. Perhaps we can put our hands together again. Thank you both.